Hello, here's the optional view video to give you a little bit of push on the homework if you need somewhere to get started or maybe just struggling a little bit. I'm not going to go over every single problem, but just kind of give you the general idea of how the homework should go. A little bit of it's pretty similar to what you've done before. Other bits maybe a little bit different, but well, we don't do the same thing every single time. And so here you can see the first few pages since I have large screens on my home computer. What we see here is the first page that's not designed to be too difficult, simply determining the lifting condensation level for a parcel at 20 degrees and 8 degrees. So we know that if the dew point is less than the temperature, that it's unsaturated, and so we cool at the dry adiabatic lapse rate, and we find our LCL height. Here we increase the parcel dew point by 5. You don't necessarily need to do the calculation. It may help you to do the calculation, but explain what would happen to the height of the LCL. In other words, where would we reach a point of saturation? A couple different parcels here where we have a temperature and a dew point of 15, a temperature and a dew point of 10. This one you have to think for just a bit. Which one would cool more during its saturated ascent? What this is related to is the fact that our moist adiabatic lapse rate is not a constant. So think a little bit about that, and this deals back to our saturation vapor pressure, that curve that I've given a funny name to, the Clausius-Clapeyron relationship, a couple of times. Which gets us to pages 2 and 3. Here we have some data from our class Radiosonde launch. And I've had to, well, to be fair, manipulate the data just a bit and have a couple of just not necessarily exactly what was happening that day to help it work out just a little bit. And so here in the first one, I want you to fill out the temperature and the dew point. Note that we have the heights here, 0, 500, 1,000, 1,500. So somehow the LCL is going to fall between 1,000 and 1,500. Again, keep things simple in terms of the dry adiabatic lapse rate being 10 degrees Celsius per kilometer. Your moist adiabatic lapse rate, as we put up here, assumed to be 5 degrees Celsius per kilometer. So again, the biggest thing is make sure you're just doing your math right in here, since you're going to have to deal with fractions of a kilometer within this portion right here. Also, be sure to circle the parcels that are unstable relative to the environmental temperature. Remembering when we talk about an unstable parcel, it's simply warmer than the environmental temperature. Here is your environmental temperature. And so again, this is real data, so it doesn't work out always the exact way that things play out in our textbooks or in even our labs where we've designed the material to be specific to try to highlight some points. So the real world never behaves exactly as you want it, but it actually also makes it more interesting because now we can kind of realize that this is how the atmosphere is really working. And so here we're going to say that we artificially lifted the parcel because in reality, it wasn't a day where we had a lot of lift going on. And so you want to think about clouds that it might produce. Think here in terms of, do we have any layers in which the parcel is warmer than the environment, or are we going to simply have to force things upward without any periods in which the parcel is warmer? Give it a little bit of thought, especially remembering that the clouds are going to happen once you reach the lifted condensation level. Number 6 is simply taking what happened in the morning and tweaking it a little bit for what may have been happening later in the day. So we have our here in the morning, 23 degrees Celsius temperature, 12 degree dew point. Here we warm it up about 5 degrees and also add a little bit of moisture to our parcel. And we go through a similar process of finding our LCL and then finding again where we might find some clouds. And would the clouds be any different in the afternoon hours? That gets us to the second portion of the homework assignment, Part 2, Stability and Thunderstorm Summer in Mobile, Alabama. And so these are going to work off of the graphics both on page 6 as well as page 7. And so again, I hate to scroll too much. You'll notice here on page 6, this is taking place at 12Z on a date in June 2002. That's going to equate till 7 in the morning. This graphic is going to be at 0Z, 7 p.m. So this is morning. This is late afternoon, early evening. And so what you have in each of these graphics is you have one line here, solid with the little squares on it that's indicating your actual temperature of the environment. You have this lighter triangle notched line, little dashes here as well, showing the environmental dew point. You have another dashed line showing the dry adiabatic lapse rate. And then you have a solid black line that you'll see follows the dry adiabatic lapse rate low in the atmosphere before changing. The idea that it then hits a point where we reach saturation and we rise then at the moist adiabatic lapse rate. And so a lot of the questions here are going to deal with how does that parcel path relate to your temperature. In other words, are there periods where, maybe your parcel is cooler than the environmental temperature? Again, look at your x-axis. This is going to be your scale in terms of temperature. And then maybe there's other areas where, maybe my parcel here at 6,000 meters is around 0, but my environment is maybe like minus 12. So here we have the parcel much warmer than the environment. Again, I'm simply giving you food for thought to get you through a number of these. And so the one thing that I'm going to really strongly recommend you look at to help you through this portion of the homework is your last lab on stability. Look, for instance, at how we indicated whether a profile was stable, unstable, or conditionally unstable. For instance, when we didn't consider moisture, in other words, the entire time it cooled at the dry adiabatic lapse rate, and then a second time we considered moisture where we hit a lift in condensation level, and we then cooled at the moist adiabatic lapse rate, were they different in regard to the temperature of our parcel versus the atmosphere? And that would determine whether or not, again, we were in an entirely stable or an absolutely stable environment, an absolutely unstable environment, or if they were different, it was a conditionally unstable environment. So give that some thought. Heights that parcels need to be lifted in order to become buoyant. Buoyant meaning they're going to want to rise unassisted. And so did this ever, hint, hint, it does reach a point in which the parcel becomes buoyant. It's going to want to rise because it is, this may give you a little bonus hint, unstable relative to the environment. We've already kind of talked about that here. So if you need to rewind a minute, and you get to listen to my voice for another bonus minute. We'll determine whether or not that makes you a winner or not. Again, do this then for 0Z. Note that there's going to be a little difference in the height at which it needs to become buoyant. Think about whether or not we're going to have deep clouds such as cumulonimbus or shallow layered clouds such as nimbostratus. And then again, some general questions that are going to relate to what's going on if things were slightly different in some instances. For instance, if the low levels were drier, how would that affect the height at which we reach condensation? In some ways, I'm hopeful that as you work through this, certain questions such as number 15 start to become a little more apparent. If we have drier conditions in the low levels of the atmosphere, that surely is going to affect the height at which we can get condensation to occur. And so you have to think of a few more things here, and that gets us down to part 3. Part 3 is going to be different than most of the ways in which we've looked at stability. In many ways, we usually look at stability in these profiles and environments that, are looking at more of a thunderstorm scenario, cumulonimbus clouds. And so here we're looking at Green Bay in December of 2001. And so what you can note here on pages 8 and 9 is you have two different profiles, one at Green Bay, Wisconsin, the other over Lake Michigan. The big difference being the temperature and the dew point of the parcel over Lake Michigan being much warmer and more moist than the one over Green Bay. And that's, again, based upon the modification that's going to occur due to a warmer and, not surprisingly, more moist lake in many instances. Although not important specifically to this lab, this is in some ways the precursor for some of our lake effect snow setups. And so you'll notice here in the Green Bay, we have a number of layers here at 100, 500, 1,000, 2, 25, 37, and 5,000. I know it's a little goofy. Again, we're looking at real data, which means it doesn't necessarily work as clean as a lot of our canned data that we would use in a lab. But that makes it, again, a little more interesting because it's actually more realistic here. So you need to fill out the parcel temperature. The biggest thing I can stress here is be really careful in terms of how far are you actually rising. The fact that I just alluded to it. I mean, here you got 1,500 to 2,000. You may then have to go from this, let me look really, really close, 2,000 up to 2,500. But then you got to go up 1,200 meters after that. Make sure you're doing the math in a way that is actually proper given what heights we're having you look at here. And so you have to do that, figure out the stability of that profile. Again, remembering when we're determining stability, we're looking at that parcel temperature relative to the environmental temperature. What type of weather might we expect? And then here for Lake Michigan, again, be cognizant of the increments of height, 0 to 1, 1 to 5, up 500, up 1,000, and then we go up 3,000 in the last one. So big differences here in terms of the height. Consider what may have changed. If you are thinking to yourself, boy, I bet you something changes, otherwise why would he have me do this? You're on the right path. Something is going to change in terms of the stability of the low levels after this temperature and dew point increase notably over Lake Michigan. So again, that's about 10 minutes to get you started on this or hopefully help you along. Feel free to come with other questions, and best of luck. Have a good weekend, and if you see this before Saturday, hope you have some fun trick-or-treating or handing out candy. Take care.